All right, it's 7:30 Pacific. Today is Friday, October 22nd, and I'd like to welcome everybody to our webinar series. Today we're switching gears a little bit, and we're starting to talk about data science and how we can organize the data that we produce inside the platform using modeling and simulations to make the transition to the data-driven science, to the science that can help us through artificial intelligence and machine learning. So today, Alex is going to tell you about the approach that we take regarding categorization of different models that we apply in the platform and how we make the data ready for the applications of artificial intelligence and machine learning. With that, Alex, the floor is yours.
Right, thank you, Timur, and also hello and welcome to this instance of the webinar from my side. My name is Alexander Zech. I'm a postdoc at UC Berkeley and also work with Exabyte. And today, as Timur already mentioned, I will talk about data structures and specifically the CateCom approach, which is the data-centric model categorization scheme. All right, so then the outline the agenda for today. So first we will cover some of the background. I'll introduce the main entities that we see in computational research and also the data formats that are used to represent those entities. And then we look at some schemas for material modeling entities. Then I will introduce the CateCom approach, specifically the architecture and some schemas and examples. And at last, we will look at the big picture, how the CateCom approach fits in the FAIR data infrastructure, and then also look at the model material and property relationship. And finally, the impact on the Exabyte platform, having this new data standard. And then there's some time for Q&A afterwards. All right, so first of all, let me say a few words about the Exabyte platform. Exabyte is a platform material research, material science research and development, and with a specific focus on data-driven discovery. So that means that we'll provide a common space for data scientists, experimental scientists, and also computational scientists to work collaboratively on the same problems. And if you would like to learn more about the architecture of the Exabyte platform, Timur prepared a manuscript that you can find on arXiv here. And I would also like to point out the YouTube channel of Exabyte. So this is where we collect all the webinars, also this one, and other instructive material, how to use the platform or how to, or giving an overview of the platform. And yeah, you're more than welcome to visit the YouTube channel. Oops. So now, then starting with the background. So throughout history, scientific discovery has passed through several paradigms. So starting with the kind of experimental science and then moving over towards the like theoretical description of the observations. And then finally at the beginning, or like around the 1950s, we also moved to the computational simulations of these observations. And right now we are in the basically shifting towards the fourth paradigm, which is data-driven science. So we have vast amounts of data that we would like to analyze using big data techniques such as like pattern detection in order to extract knowledge from this amount of data. And that also requires that we treat data in a unified way. And recently, people have come together to develop a data guideline, which is known as the FAIR data guiding principles. And FAIR here stands for findable, accessible, interoperable, and reusable. So these are the requirements that we would like to put upon the data and also data structures that we use in data-driven science. So in computational research, there often emerge certain main entities. So in principle, we have a job that we're running out to get a property. And we would like to represent these entities also in terms of data. And so the job, for example, could hold information about the high performance computing infrastructure, but it also holds other key entities that are needed for the simulation. So obviously we want to know about the material that we're simulating. So this is one entity. Then we have the workflow, which contains a sequence of tasks that are executed in the job. And then there is the model that we apply to the material, and that also determines the accuracy of our simulation. And then we have a method. This represents how we solve the model. So this could, for example, be a plane wave basis or atomic orbital basis. And this will determine the precision of our simulation. So all these data structures we would like to, or these entities you would like to represent as data structures. And today's will be mostly about the model data structure. So I mentioned categorization in the beginning, and why are we interested in categorizing the models? So first of all, by giving our model data structure more dimensions, we can organize it in a more structured way. And in this way, we can avoid having duplicates in our computational research. It also enables us to capture more complex model data. So you can think of, for example, like a custom functional where you tweak some parameters that can be covered with such an object. And secondly, this will also facilitate data-driven science and its usage with machine learning techniques. In particular, we are interested in identifying like successful combinations of material, model, and property. And in this way, eventually we would like to automate physics-based property predictions. So this would move us one step closer to an AI chemist in the cloud, or maybe something like Jarvis that you know from the Iron Man movies. So right now, models are often implicitly categorized and often represented as a string. And there's also good reason to do that. If there's a very homogeneous database, there's no need to save redundant model data because it can be implied. But there are also other concepts, for example, the nomad meta info, where we have like almost like a network of information points, like the electronic structure method, for example, is also represented as a string, but it also contains information about the exchange correlation functional. And mostly we represent this data as JSON objects. So I quickly would like to introduce JSON a little bit. So JSON stands for JavaScript Object Notation. This is basically a collection of key value pairs, and the JSON data type contains built-in typing. So a value can be a string, a number, a Boolean, array, or an object itself, or a null type. And this is a very popular data interchange format. So it's not only, as it already implies, supported by JavaScript, but it also contains, or it's also supported by other languages like Python, C++, etc. So really a lot of languages that support this data structure. And we should also mention the JSON schema, which you can think of as a blueprint of data structures. So this is how we describe our data. And this can be used in order to enforce consistency of the data structures in the database, and also to validate our data structures. So best to show this with an example. So let's assume I would like to create a data structure for an atom. And I would like to have certain keys, for example, the symbol, the atomic number as an integer, and then an array of coordinates. So I have to define, first of all, that it is a object, and then all the keys will be collected under the properties. And for each key, I define a certain type. So if we now create two JSON objects, you can see that the first one would be validated. So this would work because all the types are met. So we have a string, integer, and an array of 3 numbers. But the second one would not work. And this is already for 2 reasons, because the atomic number here is represented as a string, not as an integer. And we have a false number here appearing that would violate this max items flag. So you can see that in this way, we can precisely describe how we would like our data structure to look like. And this is also used on the platform to describe all the entities I was mentioning earlier. And these schemas that are used on Exabyte platform are collected in a repository called the Exabyte Source of Schemas and Examples, or short SE. This is available as a Node.js or a Python package. And it's an open source repository. So if anyone is interested, they can check out these schemas there. There are also examples for these schemas. And this is also a collaborative approach. So if anyone is interested in contributing new schemas, having some ideas, this is certainly possible, and you're more than welcome to. All the entities that I mentioned earlier are represented as schemas in this repository. And not just those entities, but also more primitive ones, such as a schema for an array or literature references you can find also in this repository. So with that, we come to the CateCom approach. So our design principle here is that we would like to represent as many details about the model as possible with this data structure. And we do this first by decomposing the model into reusable components, which we call unit models. And in this way, we want to create a basis of unit models such that a given model that is used for the simulation, which we call here a compound model, can be represented as a vector in this unit model space. So this is a very flexible approach, and we are able to reuse some of the components in different contexts. For example, the compound model could involve several software packages. So this would be no problem at all. And also we could represent non-standard or some customized models that like combination of unit models that people would not think about immediately. And these unit models are currently, our working definition for them is that they are the smallest logically consistent set of equations or operators associated with a central property. So it means we draw some line how to separate a given model into unit models. And an example for that would be perturbation theory. So in perturbation theory, we split our Hamiltonian into an unperturbed Hamiltonian that we can solve exactly, and the perturbation. And the unperturbed Hamiltonian, when we solve it, we obtain a set of orthonormal eigenvalues and eigenfunctions, which are then used to express, to develop the perturbation in series. So also these eigenfunctions we usually obtain from mean field theory as well. So we can think of the first part as the first unit model as being mean field theory. And then the second part, like applying these eigenvalues and eigenfunctions to the perturbation theory expressions, this would be then the second unit model. So although we think of perturbation theory as one model, we can really split it into 2 unit models. And especially the mean field part can be reused in different contexts. So it doesn't have to be perturbation theory. You could also think about ab initio wave function methods like configuration interaction. So the hierarchy of the unit model categorization follows a certain structure. So we start with 3 levels, which we call tier 1 to tier 3. This is where we assign a given unit model to model families. And after that, it will be more specific with type and subtype. And the hierarchy also follows an object-oriented approach in the JSON schema. This is realized by the all-of operator, which enables us to include a schema in a current schema. So here an example is that we have, let's say, a schema for the tier 3, and we include the schema that was defined in tier2.json. And in this way, we can propagate information down the model branch, basically. So our hierarchy for the first 3 tiers, you can see here, it's basically 2 model branches. On the left, we have the physics-based models, and on the right, the database or statistical models. And I will not go through all these models in detail, but best to look at an example. So if we have, for example, the DFT method with a GGA functional, we can follow the first 3 tiers. So DFT is a physics-based model. We will put it in the quantum mechanical category as we're solving the Schrödinger equation and having explicit expressions for the electrons. And density functional theory has in this tier 3 its own category, since it contains many flavors of DFT. And then we specify that we use the Concham type of density functional theory. And then furthermore, the subtype would be the GGA, the generalized gradient approximation. So apart from the categorization, so the 3 tiers and type and subtype, we also include tags in the unit model data structure. So this allows us to capture other dimensions of categorization. So for example, we could categorize a method, a model as a single reference model or multi-reference model. And by using tags, we can capture these dimensions. For example, if a model is able to produce excited states, or if it was obtained self-consistently, these may all be valuable information for sorting or searching. And for database models, for example, it could be a tag like indicating that it's a supervised or unsupervised learning method, or something like regression could also be included as a tag. And since categorization is a non-unique problem, there are different ways of categorizing. We devised classification rules in order to guide contributors how to add new models to this model tree. So this would be good guidance for newcomers. And maybe then we move to examples of the data structures. So this would be an example of the unit model. We have here, so basically there are 3 elements to the unit model data structure. First of all, we have the categorization that we already introduced. So tier 1, tier 2, tier 3, type and subtype. But there are also 2 other parts. Next one would be additional data. For the unit model of density functional theory, this additional data is right now just the functional. So in the specific examples, we have the PPE functional, and we don't just only represent the name of the functional, but also its components. So we can capture a lot of information here about the functional. This is obviously a bit simpler example with 2 components, one correlation component and one exchange component. But the definition of the components also supports, for example, hybrid functional, where we add fractional amount of exact exchange, or range separated functional. This is all possible to express accurately with this type of data structure. And then finally, we have metadata about the unit model. So this includes unique identifiers, tags, as I mentioned before, then references. This would be reference to literature, and the method object, which I will explain on the next slide. So again, the method object holds all the information, how we solve the model, and in the specific example would be like a pseudopotential plane wave method. And apart from a simple categorization of the method, we also list all the non-default parameters that are used here. And here in this example, it's the kinetic energy cutoff for the charge density. And these parameters are also labeled. So again, we contain the name value, the unit of the value, and then also labeled categories for this parameter. And in this way, we would like to identify precision parameters. So these are parameters that are important for the precision of our simulation. And then we collect them here in this next field that's called precision. And the method object is also able to hold more like raw data. So in this specific example, we could have the coefficients for the pseudopotential itself saved in this method data structure. And then finally, the compound model is more a lightweight data structure, since we do not need to repeat the information from the unit models. So it will hold only references to unit models, and we can in this way construct a model graph, which I will get to in a second. But apart from the model graph, we again contain a name, identifiers, a global method object. This will contain method parameters that affect all models, all unit models simultaneously. And again, tags to keep more information about the compound model. So the model graph, you can see here, pictorial definition. This will be an example where we first run conjunct DFT and then use the results to run a GW, and then finally run the solve the beta equation. And so we have this like directed acyclic graph of unit models that is represented in the model graph, but the model graph also holds information about the workflow units. So what program was, for example, executed in order to run the unit model. And so this would go back to what I mentioned earlier, that we can use different software implementations for one compound model. So let's have a look at the big picture. So first of all, I would like to talk a little bit more about how the CateCom approach fits into the FAIR infrastructure. So since we use unique identifiers for the unit and compound models, these become findable and searchable. So this would fit in the aspect of the findable part. And regarding accessibility, so this has a lot to do, for example, using available data standards. Again, we meet this requirement by using JSON, which is very commonly used. And then regarding the interoperation, there are several possibilities. So first of all, we would like to interface with other material databases. And regarding the model object, this could be just populating a model object from a string that we obtain from a database. Or if there's more information available, we could even try to map between schemas. And secondly, the categorization approach that we use in the unit models is very similar to what's being done in ontologies. So for example, we have the materials design ontology or the elementary multi-perspective materials ontology. And since they, like the taxonomy or categorization that we have here shows a lot of similarities, we could try to interface it with these ontologies as well. And this would allow us perhaps to run semantic queries or to construct something like knowledge graphs. And then lastly, by the unit models itself are reusable. So this would fit into the aspect of reusability. but also enriching our unit models with data makes them reusable in the sense of that we know where the data is coming from. All right, then the model categorization is really only one part of a greater concept. So if we look, for example, at a model like LDA, so we know it's great for some properties, but not for all properties. So, for example, the band gap with LDA is like seriously underestimated, and so it would be important to find combinations of model, material, and property that give us great results. And this requires us to also categorize materials and properties. And so this has a few reasons. So first of all, we need to reduce dimensionality. So if every material is treated at the same level, the chemical space is just too vast in order to find these relationships. And also by categorizing the material and property as well, we can then construct associative relationships. All right, and then I'd like to go into a little bit of the roles or the impact that this categorization has on the roles on the exabyte platform. So first of all, we have simulation experts that know how to run these calculations. And we would like to be able to reuse the model information or the model settings that they are using, so that, for example, simulation beginners or material science experts can then use these expert templates right out of the box. But also, if we keep a lot of the information about the model settings, and this would tie in to the slide before, we could think about an automated model setup. So if we are able to construct these associative relationships, we could say that given a model, given a material and a property, we could suggest a fitting model. And then on the other hand, we have data science experts and material science experts that know how, like what data structures are important and how to construct them. And these can be considered contributors to SE. And then finally, in the machine learning part, we have machine experts and material science experts that are then able to save the basic, or like track the basic settings for machine learning on the platform with these model settings. And this tries to it's important to understand the model, and because right now there are not a lot of ways to save the machine learning information in a standardized way. And so by having an objective way of representing the model data, it would be beneficial for a lot of the users on the exabyte platform. And finally, then we could involve the community also to curate the data on the database. So with that, I would like to summarize, and then we can go over into Q&A. So first of all, we introduced a new model data structure containing a practical categorization scheme that also fits in the FAIR data infrastructure and is a very flexible approach based on these unit models. It is still work in progress, so we would like to invite people to contribute to this endeavor, and especially because categorization is a notoriously difficult problem. One has to be very proficient in these models in order to categorize them. So it makes sense to invite the community to extend this categorization scheme. And then finally, there are always things that can be improved. And right now, we're interested in improving the interoperation of unit models. So for example, we would like to be able to restrict certain combinations of unit models automatically. So all this information about the unit models and compound models we have summarized in a manuscript that you can find on arXiv. And yeah, if interested, please also check out our GitHub and our YouTube channel. And you can follow us for news updates on Twitter. So with that, I would like to thank Timur and James, who have been working with me on this project, and of course, the whole Exabyte team. And yeah, thank you very much for your attention.
Thank you, Alex. This was a good description of our recent work. Again, I'd like to focus the attention of the audience on that article that Alex just demonstrated. That's where we explain the approach in more details. This is still work in progress. We're still iterating very quickly on it, but we would like to collaborate, and that's the reason why we made the approach open source and open access in the first place. I don't see any questions in the chat or in the Q&A session yet, but let me maybe start this discussion with the reason why we have the data structures is to be able to organize the information that comes from our users. And maybe we can speak a little bit about these upcoming features that we're working on, like the workflow designer.
Yeah. So then go back to maybe this slide. So you mean this part? So
right.
I mean, yeah, this goes back to what we mentioned in the beginning. So that given a like if we are able to construct these associative relationships, we can think about automatizing the model setup. So like suggesting a model given a material and property, and yeah, I mean, yeah, making it easier for simulation beginners to set up the calculation.
Right. So we're planning an overhaul to the workflow design system that we have today, and this overhaul will include significant extension to be able to track and understand the input that expert users that today work on a platform bring. Right. Most of the time, expert users produce either a shell script or a Python script that, or maybe just edit the input files for simulation engines directly. And it becomes very difficult to understand the exact setup, the models that we use, the method parameters, the precision. And our goal is to try and decouple and make all of that much more visible, much more easier to organize. And then with this data input from simulation experts, we are able to build this data set that tells us that a particular model gives good precision for a particular property, right? And that's how we enable the brain icon that we have inside this diagram by having input from a global community of simulations experts. And our idea is that to be able to have something like that, we first have to really understand the domain and the data sources and the kind of data that we're dealing with. And machine learning comes on top of all of that. Yes. I just wanted to verify this a little bit more. I have a question here from an anonymous attendee. The question says, where can we access the database of ConShem DFT results for material studies and property prediction? Would you like to take this question, Alex?
Yes, I mean, in principle, all the information is saved on the exabyte database, right? So the what I mentioned earlier, the categorization. I mean, right now, you can already find ConShem DFT results on the database. It's just that with the new categorization scheme, it would be easier to identify which, for example, which approximation was used for the ConShem DFT results. Is that
Right. So in our platform, we have a global, we have this concept of data bank, and it usually applies to materials and workflows in our case, and properties as well. And we have collections of materials and simulation results that are specific to a certain account. And then we have a platform-wide collection where we organize all the publicly visible data. So if you go to that page in the platform, you are able to see the content that other people have shared. And that's one way to access all the information. If you want the programmatic access that you can get through RESTful API, and we have Python-based and JavaScript-based access to the RESTful API so that you can get multiple entries and you can work with things like Jupyter to build models and to organize all this data inside that environment. I hope that's helpful. Please let us know if you have follow-up questions on that. We have another question from anonymous attendee as well. How can we contribute simulation results to the data set, to the database?
Yes, so just go back to, oh, sorry, this is down here. There we go.
Maybe the diagram,
yeah. So as I mentioned earlier, all the schemas are collected in SE, in this repository on GitHub. And a contribution could look like the following. It would follow basically the standard like contributions on GitHub. So this would be by forking the repository, then introducing new implementations, and then finally asking for like a pull request. And so in this way, it can be done collaboratively, so people can see the changes. It will all be discussed and done openly. So yeah, so this is one way to contribute.
So when we speak about contributions, there are multiple ways to.
Oh, and also, yeah, sorry, yeah, the results as well. I mean, for the results, you would have to sign up on the Exabyte platform and run calculations.
Right. So either we should come back to the diagram that we had at the end. I think we tried to explain different ways to contribute inside this diagram. Either you can contribute results directly by using the platform, and that's why we work on this new version of the user interface to be able to automatically organize the data. So when you produce new calculations, the data underneath is automatically organized, and the CateCom approach is deployed there. Another way to contribute data is to use it's Python-based toolchain. We have a tool called ExaParser that today can accept data from Quantum Espresso and VASP calculations, and it can help organize this data inside a database. So if you have local directories or directories on some other high-performance computing system that you executed calculations in, then you can use this tool to upload important information like material structures and the properties that were calculated during this simulations to the Exabyte platform. And then after that, you can use our RESTful API to retrieve these properties back and to have them stored inside the standards that we deploy. And then the contribution that Alex was speaking about is more on the data science, when people want to contribute specific kind of properties or additional types of data that we want to support. We welcome that as well. And that's why we made the repository itself open source and available on GitHub. All right. I hope that was helpful. Please let us know. And we have a couple more questions. I have a question from Robert. Interesting work. Thank you. What might be interesting for future webinars is to walk through a specific model, real world example. Yeah, just a thought. Absolutely. Yes, absolutely. Yeah. This is, we're just starting this work, and I think we wanted to bring attention to it from the audience. We may have a follow-up where we explain how this is used in practice.
Yes.
We have another question from Jitendra. So how can one calculate the volume corresponding to total energy curve using DFT if you have not obtained the parabola type curve? Wow, that's a rather specific question. I would suggest taking this discussion by email. And please contact either myself or our team. You can contact me at timur@exabyte.io or our team at info@exabyte.io. And we can take this discussion by email. Because it falls a little bit outside of the focus of today's webinar. All right, did I forget anything else? Any other questions in the chat or in the Q&A? Looks like not. All right. Thanks very much, everybody. Thank you for joining us today. We'll be back next month, and we will follow up with the presentation for today and the live recording as well on YouTube. Thank you, Alex. Thank you all the participants. See you next month. Bye.
Bye.